All right, welcome back. We have text problem 23-13 up for today's video. As always, get out a scratch piece of paper or a blank printout of the problem. I do have to apologize. The Wi-Fi network here in the building was not working very well, so I couldn't upload the text to the problem, but I will quickly read the problem for you all. The electric field in a certain region of Earth's atmosphere is directed vertically down. At an altitude of 300 meters, the field has a magnitude of 60.0 newtons per coulomb. At an altitude of 200 meters, the magnitude is 100 newtons per coulomb. Find the net amount of charge contained in a cube 100 meters on edge, with horizontal faces at altitudes 200 and 300 meters. All right, so from that reading, the biggest thing is the net charge contained in the cube. Another way of describing is the charge enclosed by this cube. As soon as you see enclosed, it should scream Gauss's law. So if we have that, we're going to need to choose a volume whose surface area will help us identify our Gaussian surface for the problem, or the enclosed surface that will help us tackle the problem. All right, so again, read step, we see that we have enclosed charge, and we're going to need to use Gauss's law. Now for our draw step, this is extremely important because as we choose a volume to contain a charge, then we need to be able to describe how that is interacting with the electric field. So in the problem state, we're given the fact that we're looking at a charge contained inside of a cube. So we're given the volume and how it is described in its shape, but that may not be the case for every single problem. You have to choose the shape that makes the problem as easy as possible. Okay, so for this problem, we're told it's a cube. It's the easiest way to go about this problem when we're looking at a difference in height. All right, so now that we have our shape outlined, we want to make sure that we identify the different vectors we have at play. We have our electric field, again, is directed vertically down. And most importantly, the electric field is dependent on its vertical position. So at 300 meters, the magnitude of the electric field is 60.0 newtons per coulomb, but at 200 meters, it's 100 newtons per coulomb. So it's dependent on the height. All right, the other vector we have listed in here that we have to be able to draw with any Gaussian surface is the direction of the differential area. Now, what I'm going to do is I'm going to copy this figure, and when we get to the solve step, I'm going to pull it back up because I'm going to lay out the direction of each of the differential area vectors and what they actually mean. So it's going to be important to reference the picture. So make sure that when you're taking your notes on this problem, make sure to have that picture handy as we get into later steps in the problem. So we're given the electric field at the different altitudes, which I just mentioned, and we're given the fact that we have a cube that has a 100-meter length, width, and height. All right, so we do have a cube. Now that's all we're given for this problem. All right, so for our assumptions, the great thing about using Gauss's law is that when we say things like a closed and isolated system, by using a Gaussian surface, we have essentially made the assumption that we have a closed and isolated system. All we care about is the charge enclosed inside of our Gaussian surface. Anything outside will have no bearing on the problem at hand. Okay, so we don't have to make any additional assumptions, because by saying we're going to use Gauss's law, we've covered all of our bases. All right, so for our tasks, we have to determine the net enclosed charge, or the charge contained in the cube. But for us, that just means calculate Q enclosed. All right, physics step time. That's where you pause the video. You write down the equations you think will be necessary to complete this problem. And I will see you in about 1 or 2 minutes. All right, welcome back. So, how'd you do? Well, I think we're going to need 2 equations for this problem. The first one being, of course, Gauss's law. And if we dissect this, we see first this symbol that you may have never seen before, but it describes an integral over a closed surface. That's what that little circle means right there. So when we look at this, we have the closed surface integral of our electric field vector dotted with our differential area vector. Okay, so when we say closed surface, that means you have to look at the vector, differential area vector, pointing in every direction on that surface. Okay, so as we get to this picture, we can describe that, well, for the surface area of a cube, how many sides do we have? Right, we have 6 sides. Well, one differential area vector is not going to describe each of those surfaces. Each surface will have its own differential area vector. And that's why we have a closed integral. That means that we need to do an electric flux calculation on each surface of our volume. Okay? And that will contain the charge enclosed. So we had to add them up. All right, so as we draw a picture of where all these differential area vectors are, we have one for each face. So we have one right here. That would be our differential area, and you can call it differential area T for top. You have one here on the side. That is our differential area, and we'll say S for side. And how many sides are there that are not the top or the bottom? We have 4. One pointing to the right in the positive x direction, one pointing to the left in the negative x direction, and one pointing into the screen and out of the screen, or the positive and negative z direction. So there's 4 of those. And so we have top, 4 sides, and our differential area vector for the bottom. All right. So I'm going to put a note here, 4 sides. That reminds us that as we look at our Gauss's law equation during the solve step, it's not just one side, there's 4. All right. The other equation that we're going to need is our connection between the dot product using vectors and the dot product using our magnitudes and angle. All right, so that's on the back of the PRC in the lower left-hand corner. All right, that's going to help us visualize how the electric field interacts with each of our 6 surfaces. Okay, now this is a difficult concept, and I understand. On the next slide, we'll go nice and slow through it deliberately. I strongly encourage you to take your time deliberately going through text problem 23-22, I think is the other one, just to get some familiarity with dealing with a volume here, or that we have a cube volume on 23-22, it is a long wire where you have to use a cylinder as your volume. And it just gives you practice dealing with different geometries. Okay, so let's go to the next slide and we'll begin the solve step. Okay, so here we are. We have our drawing here on the right. We have Gauss's law here right next to our solve step. One of the points that I failed to mention that's extremely important is how to know which direction your area vector points. The differential area vector always points normal to the surface. So in this case with our cube, our differential area vectors always point away or out from the cube, normal to the surface on each side. So for our differential area vector at the top, it's pointing straight up, normal to the surface. For our sides, the same thing, normal to the surface, it points for that specific side off in the positive x direction. And then for the bottom face, it points directly down. Again, normal to the surface, but it's always easy to say that it points away from the shape, normal to the surface. Okay, with that being said, let's get into looking at maybe something you're unfamiliar with or just seeing for the first time. And that is this closed surface integral. All right. The easiest way to understand how a surface integral works is to say to yourself, I have a volume I've chosen, and for each surface on the volume, I can look at the electric field pointing through that surface. So in this case, we have a cube. And we have to look at the electric field pointing through each of our surfaces. Well, we have 6 sides on this cube, so we need to break down the electric flux, which is the electric field through an area, for each of our sides. So it's almost like looking at a vector in that we can break it into its x and y components. Here we're breaking our surface integral into its surface components. So for our cube, we have 6 sides. We will have 6 surface integrals to do. So let's break those out. We can start going from top to bottom. We have our integral of the electric field at 300 meters, dotted with our top differential area vector, plus 4 times the integral of our electric field. Now this is going to be at varying heights, but you'll see that it won't matter. Dotted with our side differential area vector, plus the integral of our electric field at 200 meters, dotted with our differential area vector at the bottom. Okay, so we've broken a fairly condensed equation into a very elaborate equation, and I didn't quite finish it. That's all equal to the enclosed charge over the permittivity of free space. Okay, now let's look at each of these integrals individually. Well, we said that we're going to need 2 equations for this problem. We have our generic form of the dot product expressed in magnitude and angle form. Let's do the same conversion for the integrals that we have listed here. So for our first one, we have the integral of the magnitude of our electric field at 300 meters times the differential area, the top, and again that's just the magnitude, times the cosine of the angle between those 2 vectors. I'm going to call it theta sub t. plus 4 times the integral of the magnitudes of the electric field and our differential area vector on the side. The magnitude of our differential area vector times the cosine of the angle between those vectors. And since all of these sides are the same, and we can say that because the electric field is pointing directly downward, so our side differential area vectors are all going to be the same angle between the vector of the electric field. So we'll call that one specific angle, theta sub s, plus the integral of the electric field at 200 meters times the differential area on the bottom times the cosine of the angle theta sub b. Bleeding over a little bit there. Okay, now how do we figure out what each of these angles are? Well, I'm going to do one for you, and then I'm going to ask you to do the same for the others. So I'll start with the first one. Our electric field is pointing down. Electric field at 300 meters. And our differential area vector for our top surface is pointing normal and away from the surface. So, angle between our vectors is 180 degrees. All right, now I want you to pause the video and do the same vector diagram for our side, just one side, and our bottom. And I will see you in a minute or two. All right, welcome back. You may not have been able to use fancy colors like me, but hopefully your vector diagrams look similar. All right, so for our side differential area vector versus our electric field, you should have noticed that they are 90 degrees apart. And that doesn't matter which face you're looking at on the side, whether you're looking at the one facing the screen, the one pointing in the positive x direction, the one pointing in the negative x direction, or the one pointing into the screen. It doesn't matter. The electric field is 90 degrees from each of those vectors. And for our last differential area vector, the bottom area surface, or the bottom surface, we have two vectors that are actually parallel. So the differential area vector on the bottom is pointing in the same direction as the electric field. So theta sub b is equal to 0 degrees. Now we can apply each of those to our cosine term. And we should know by now that the cosine of 180 degrees is, drum roll please, -1. And if you need to see a pretty diagram where this is my angle theta and this is cosine of my angle. At 0 degrees, cosine starts at 0, dips below, and then back up. So here is theta is equal to 0, and here is theta is equal to 360 degrees. Guess what? Right here, at theta is equal to 180 degrees, we have -1. And at 0 and 360 degrees, we have +1. Okay, so if we go from +1 at 0 degrees to -1 at 180 degrees, what is the cosine of 90 degrees, or halfway in between? It's right at this point, right here. Cosine of 90 degrees is equal to 0. So let's write those out. So this is -1. This is 0. And for our bottom component, again, cosine of 0 degrees is right at this point. It is positive 1. Oop. Color swap. All right. Notice that we were able to simplify the problem just analyzing the direction of our electric field compared to our differential area vectors. So all 4 sides that are not the top or the bottom have 0 electric flux, meaning there is no electric field pointing through that square. Whether you're talking about this square or that square or the one behind or in the back, it doesn't matter. It's just like trying to blow a bubble with the circle perpendicular to your mouth. So as you blow, air is going on either side. You're not going to form a bubble. Okay? There's 0 air flowing through that circle, that surface of soapy liquid. Same thing here. The electric flux through our sides is 0. All right. So there's only 2 integrals left. The electric field flowing through the top surface and the electric field flowing through the bottom surface. Now, if this were a uniform electric field, then they would cancel out and you'd be left with 0. But we don't have a uniform electric field. The electric field at the top is different from the bottom. So let's go to the next slide. All right, so here's what we're left with. We have the integral of our electric field at 300 meters through the area of our top surface. And we have to multiply that times -1 because the angle between our vectors is 180 degrees. And our other surviving component is the integral of our electric field at 200 meters through the differential area surface on the bottom, and multiply that times +1 because the angle between our vectors is 0 degrees. And that's all equal to our enclosed charge. This is what we're looking for. So we just need to finish out these integrals and go from there. All right, so I want you all to do these integrals on your own. Better yet, I will do the first one with you, and the next one you can do on your own. So for this first one, the first question you have to ask is, does it matter where in that top square I measure the electric field? And the answer should be no. Anywhere at 300 meters, I'm going to see the same magnitude of the electric field. So it doesn't matter if I'm looking at the left side of that top square or the right side or into the screen or out of the screen of that top surface, it doesn't matter. That means that our electric field at 300 meters is not dependent on where on that area I'm looking. If that's the case, we can consider that a constant. So if it's a constant, we can pull it out. The electric field at 300 meters times the integral, there's a negative here from our angle between the vectors, times the integral of our differential area at the top. What is the integral of a differential element? You could rewrite this as, what is the integral of dx? Well, it's just x. Okay? So in this case, instead of x, it's A, our area, the area of the top. So negative electric field at 300 meters times the area of our top surface. All right, now I want you to do the other one. I want you to go through the same thought process and see how you do on your own. All right, welcome back. So you should have something that looks relatively similar to our first one. The only difference is we have the electric field at 200 meters times the area of our bottom surface. Now we have a cube. That means that the dimensions on each of our sides are exactly the same. So the area of our top surface is going to be equal to the area of the bottom surface. So A sub t is equal to A sub b, and we can say that's all equal to the same area, just A. And as we identified on our last diagram, the side length, width, and height is little a, so that's all equal to A times A, or A squared. Can we have more equal signs on one line? Probably not. So now we have A squared that is shared by both terms times the electric field at 200 meters minus the electric field at 300 meters. And let's make these brackets. And that's, again, all equal to the enclosed charge divided by the permittivity of free space. Now, if we're solving for our electric field, if we're solving for the enclosed charge, then we need to multiply both sides by the permittivity of free space, such that the enclosed charge is equal to permittivity of free space times the area of each of our surfaces times the difference in our electric fields at the different heights. There is our algebraic solution. All you have to do from this point is input our given values, where this permittivity of free space is a constant. It is on the back of your PRC. The side of each of our dimensions on the cube is 100 meters, and our electric field at 200 meters is 100 newtons per coulomb, and our electric field at 300 meters is 60 newtons per coulomb. That's a difference of 40 newtons per coulomb. And so we get a solution of 3.54 times 10 to the negative 6 coulombs, or 3.54 microcoulombs. Either one works. We went with three significant figures. I know that it shows 300 meters and 200 meters and 100 newtons per coulomb with no dot after the zero that identifies them as three significant figures. But we'll assume that there's a dot there and just say, hey, this is three sig figs. On a graded event, we won't be that convoluted, so no need to worry. But there is our solution. There's plenty of practice you can do on different types of Gauss's law problems, so I strongly urge you to get some practice. We will do so in class, and I will see you next time.